Hi, everybody. Welcome back to our online virtual lessons for AP Environmental Science. My name is Dr. Sowell, and I teach APES here in Jacksonville, Florida at Darnell Cookman Middle High School. So just to warm up, normally we would warm up with kind of a question or a refresher from the last lesson, and Ms. Fassler did a phenomenal job talking to you about pathogens and human diseases, as well as LD50 and the great experimental design stuff associated with that. But because we're starting Unit 9 today, I thought we would take a second and just look at what Unit 9 is about. So I want to highlight one particular word here. So it says a central aspect of environmental science is to understand the global impact of local and regional human activities. Humans can mitigate their impact through sustainable use of resources. So I just want to highlight that word mitigate. Most of you probably already know this, but just to make it explicit, it just means to make less harsh or less severe. And so the whole point of Unit 9 is to take these big system thinking ideas and understand them in light of everything else that you've learned in the course. Some of the stuff in Unit 9 you've probably at least heard of before in terms of greenhouse gases or climate change or maybe ocean acidification. But what Unit 9 does is it allows you to take everything you've learned and put it into contexts with some very specific environmental issues. So just taking a look at Unit 9, 9.1 and 9.2 we'll discuss today, stratospheric ozone. Ms. Fassler tomorrow is going to look at greenhouse effect and climate change. And then I'll jump back in and go into the ocean with you to talk about ocean warming and acidification. Ms. Fassler will come back and look at two unique categories of species, invasives and endangereds. And then finally, I'll wrap up our Unit 9 talking about human impacts on biodiversity. So concepts like habitat loss or habitat fragmentation. So that's the kind of flow of what we're going to be doing over the next couple of videos. So thinking about system thinking about global change, we need to consider a few things in particular. And I like to use this framework. It's called Understanding Global Change. And it's a resource from HHMI Biointeractive, and I will display the link for that in just a little bit. But in order to understand these big global change ideas in this unit, the first thing we need to understand is how those systems work. How does the biosphere work? How does the atmosphere work? How does the hydrosphere work? How does the lithosphere, the geosphere work? How do each of those little systems operate naturally? And then along comes us, causes of change. Now, causes of change can be human, but can also be non-human as well. So it's nice to understand the system, what we do to the system, and then to be actually to measure changes, measurable changes, quantifiable changes. This is the evidence of those changes. What have we done, both human and non-human causes of change? But again, that idea of understanding the system, what have we done to it, and then what are the measurable effects helps me to think about these concepts. So today we're going to be looking at stratospheric ozone depletion. And if we use this framework, today's lesson really is going to start with how that system works. What does the ozone layer do in the stratosphere? Then we're going to talk about some human activities that change that system, so particularly the use of CFCs. And then we're going to look at what are the measurable effects that have resulted from that action. And in particular, we're going to focus on human health effects today. So this is the resource that I was talking about. This is a graphic showing kind of all the details in there. But this is a resource, like I said, from HHMI Biointeractive, and the link is below. And what the resource does, it allows you to build models based on those three categories of causes of change, how the system works, and measurable changes. This one, for example, is talking about ocean acidification, something that we'll talk about in a few lessons ahead. But this is a really nice resource if you're looking for a place to practice constructing system models of the ideas and issues that you found throughout the course. So I'd highly recommend taking a peek at it. So where are we going to go today? So we've got two content goals for today. 9.1, what is stratospheric ozone depletion? Number 2, what do we do to reduce that problem, reducing ozone depletion? So nice pairing here. We've just got a problem and a solution. And so clearly we're going to practice the practice number 7, environmental solutions, but also we're going to take a look at concept explanation, practice number 1. So some prior knowledge to review before we get started. So there are some things that we're going to loop back to today, and it'll be a great review. But if you're not comfortable with these topics, I would suggest taking a peek at them. First of all, the Earth's atmosphere. That's in Unit 4, Topic 4, the structure of the atmosphere. Introduction to air pollution, Unit 7, Topic 1. In particular, we're going to talk about photochemical smog today. And that's coming from Unit 7, Topic 2. So how does the Earth function? And then some specific pollutants that we've been putting into it from Unit 4, Unit 7. All right, so here's what we need to know from 9.1 and 9.2. 9.1, the first goal is by the end of this section, you should be able to explain the importance of stratospheric ozone to life on Earth. First of all, let's talk about our cast of characters here. We're talking about ozone, and that is O3. So sometimes during the presentation, you'll see O3. Sometimes I'll write it as ozone, but you need to be familiar with that. So to get to this understanding of why the stratospheric ozone is important, we are going to, again, review the structure of the Earth's atmosphere. Then we're going to make a clear distinction between stratospheric ozone and tropospheric ozone, that ground level ozone. We need to make that distinction very clear. Then we're going to, once we define those two, we're going to specifically look at stratospheric ozone. What is it doing for us? Then we're going to look at some human actions that have depleted that stratospheric ozone. Then we're going to talk about those effects, those measurable changes that we mentioned before from the model. And finally, what did we do about it? What are some possible and current solutions to combat the ozone depletion that we have caused? So as a quick review of our layers of the atmosphere, this was in a prior unit, and basically you really just need to know the layers of the atmosphere and some of their basic characteristics. So we've got troposphere, stratosphere, mesosphere, thermosphere, and exosphere. So to give us a little quick review, it's nice sometimes to hear other words than mine. So we're going to take a look at this clip from the Meteorological Office in the UK. So a nice little review of those layers of the atmosphere. I like that because it not only shows you the relative thickness or height of each of the layers, but it also points out some of the unique differences in terms of the temperature gradient that happens within each one of those layers. So now let's, and they mentioned it slightly in that video, the ozone layer. That is what we're talking about today. So we've got this thing called ozone, and I want you to think about it almost like an actor. An actor, depending on if he's in a horror movie, might act as a villain, maybe, or he's in a superhero movie and he acts like a superhero. So this one molecule of ozone is neither good nor bad. What makes it good or bad is its location. So I typically talk to my students about ozone being good up high, but bad nearby. Good up high, meaning in the stratosphere up high, bad nearby, being down near us. So let's break down bad nearby a little bit more. And this should be a review of Unit 7 for you. So in the troposphere, we have tropospheric ozone. One of the things that I always tell my students to do is never to write naked ozone. Always attach it to something. So from this point on, it might be useful for you to always write either tropospheric ozone or stratospheric ozone. That way, just by writing that term, the reader knows which layer you're talking about. So here we're talking about tropospheric ozone down toward us. Sometimes it's called ground level ozone. But this is a secondary air pollutant and it's man-made. So you should realize what the word secondary means and also that this is not a natural substance. It is one of the main components of photochemical smog. And that, as you recall, is when we have things like NOx and VOCs and sunlight all combining to make this brownish haze called photochemical smog. And the main constituent of that, or one of the main constituents of that, is ozone, tropospheric ozone. And that can clearly lead to a litany of respiratory problems for humans. So down near us, nearby, ozone is bad. But up high, it's good. This is our global sunscreen. This is what is blocking out the majority of the UV radiation. Without this ozone layer, this layer of stratospheric ozone, life on Earth as it exists now wouldn't make it. So life on Earth, the biosphere, the organisms of the Earth, including humans, have all evolved to deal with the natural levels of UV radiation that make it through the ozone layer. So without the ozone layer protecting us, we would be exposed, and all life would be exposed to more UV radiation, and that would cause irreparable damage. So just as an analogy, think about this as sunscreen. So if you took sunscreen and put it up high, actually on the outside of your body, it's a good thing. So stratospheric ozone and sunscreen are really good up high on the outside. But if you were to eat sunscreen, don't eat sunscreen, but if you were to eat sunscreen, that'd be a bad thing. So just like sunscreen isn't good or bad, it all depends on where it's located. So ozone isn't good or bad, it just depends on where it's located. Is it stratospheric ozone or tropospheric ozone? So first of all, why do we use that sunscreen? We're trying to prevent sunburns. We have some clear skin damage that can result from getting a sunburn. And remember, a sunburn isn't a result of being hot. It's a result of being exposed to that UV radiation. So the UV radiation is coming down, interacting with our skin and causing some damage. So let's take a look at this little graph here. So you can see the troposphere is this lower part and the stratosphere is here in this middle part. And we've got three different types of UV radiation coming in: UVA, UVB, and UVC. There's some distinctions between the two in terms of wavelengths, but one of the most important things to think about is UVA has the least energy, and UVC has the most energy, and that would be the most damaging. But you'll notice this large influx of ozone in the stratosphere, the good up high stratospheric ozone, blocks out the vast majority of UVC, a good chunk of UVB, and only some of UVA. So here on the surface of the Earth, we are exposed to some UV radiation. And if we get too much of that exposure, it can lead to some very specific and significant health impacts, particularly cataracts and skin cancer. So what are cataracts? Cataracts are basically a clouding over the lens of the eye. And you can see this individual in the bottom left. One eye is normal and the other eye has developed this cataract. And it can result in some pretty significant vision problems, such as blurring. It can be caused by lots of things, but UV exposure is one of those. But again, could impair your vision. In addition to that, we have skin cancers. So most skin cancers are a result of exposure to the UV rays in sunlight. That's coming from the American Cancer Society. So what is that UV light doing to your skin to cause that? Well, it's damaging your DNA. So that UV radiation penetrates your skin tissue, can cause damage, DNA damage or mutations, which can then lead to skin cancer. So it's definitely something to be cognizant of, and it's definitely something to remind us to wear sunscreen when we are outside. So just as a little review of that sunscreen and cancer risk, let's take a look at this.
It can be easy to get caught out in the sun and get sunburnt. But what is sunburn? Sunburn happens when the DNA in your skin cells has been damaged by too much UV radiation from the sun. The heat and pain you sometimes get from sunburn is your body's attempt to repair the damaged cells. The DNA damage can happen before the first signs of sunburn show up. Even though your skin may eventually feel and look healed, some cells with damaged DNA can be left behind because our repair mechanisms aren't perfect. Over time, these damaged cells multiply and can develop into skin cancer. Remember, sunburn doesn't have to be raw or peeling. For people with lighter skin, sunburn may make your skin go pink or red, or it could be irritated or tender or itchy for people with darker skin. You are most likely to burn in the middle of the day when the sun is highest in the sky. Sunburn doesn't just happen on holiday or sunny days. Sunburn can still happen on a cloudy day. Whether you're in the UK or abroad, protect your skin when the sun is strong by using a combination of shade, clothing, and sunscreen.
So life on Earth has evolved to coexist with these normal levels of UV radiation. And when I say normal, I just mean how much naturally makes it through a robust, strong, normal stratospheric ozone layer. But even with those, or even with that ozone layer, we still have risks. And if we get exposed too much, we have cataracts or skin damage. But that is normal. That is normally to be expected. Now, if we were to get rid of that stratospheric ozone layer, the risks of these things become much, much greater. And so that's what we've done. So now we're going to look specifically at the human impacts to the ozone layer. And that starts with this chemical called, or a class of chemicals called CFCs, chlorofluorocarbons. On an FRQ, you are more than welcome to use CFCs as an abbreviation for chlorofluorocarbons, but you should be familiar with both the word and the abbreviation or the acronym. So here's an example of a CFC molecule. One of the characteristics of CFCs is it has chlorine on it. And that's going to become a key thing in the story of how CFCs harm the ozone layer. So where do we find this stuff? We used to, being a key word, hint, 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 used to find it a lot in aerosols and refrigerants. It was very common to use CFCs to make aerosols like hairsprays and things like that function better. And it was a great part of coolants. So cooling systems like refrigerators would use it. So what is that CFC doing? How is that one molecule, CFC, taking away our global sunscreen? So what happens is, as soon as that CFC radiation, a chlorine pops off. So we've got now this free chlorine molecule, and that's going to be the villain here in our story, because it combines with ozone and actually steals an oxygen away from ozone. So the chlorine snatches away an oxygen and makes chlorine monoxide and O2. So if we were to stop right here, the story would be bad enough. We no longer have this molecule of ozone that was being useful. It was blocking out UV radiation to the Earth. Well, chlorine has just now broken that apart, and we no longer have that one particular molecule of ozone. But here's where the villain becomes even more villainous. So as soon as a free oxygen comes in contact with that chlorine monoxide, it snatches away that oxygen to form O2. And now look what we have back in action, ready to go again, the chlorine. So it can go right back up and do it again. So one CFC molecule could result in the destruction of many, many, many ozones because that chlorine is almost recycled to catalyze this thing again. What happened? We have a quote unquote ozone hole, or more appropriately in the context of apes, stratospheric ozone depletion. So what does that mean? So clearly we have a problem here. We would have a significant effect on the biosphere if the ozone layer, if stratospheric ozone were to be completely depleted. We would have very significant impacts, not only on human beings in terms of skin cancer and cataracts, but if we are experiencing genetic damage to our DNA from that UV radiation, so would other life forms. And so we would have lots of impacts, broad impacts from that. So that's the problem. What's the solution? So in your head, the first thing you should be thinking of, well, if that's the villain, let's ban the villain. Let's ban the use of CFCs. And that is exactly what happened. There was a meeting and an agreement, and we got rid of that evil chemical. Now, so this is really about 9.2. So by the end of this, you should be able to describe the chemicals we've used to substitute for CFCs. So we still need aerosols, we still need refrigerants, we just don't want to use those CFCs. So to get there, we're going to talk about something called the Montreal Protocol, and that is an agreement that banned the CFCs, but we're also going to talk about briefly what are some replacements for CFCs. And just like any solution, we have pros, cons, and unintended consequences. Montreal Protocol. So in 1987, we had an international treaty that agreed on global reduction and eventual phase out of all ozone destroying chemicals, such as CFCs. And you can see from the graph here, the production of CFCs was increasing. And then we have the Montreal Protocol, and we start to see it drop off. This is an old graph from 1992, so you could assume it's getting lower here. The reason we didn't see an immediate restoration of the ozone, the stratospheric ozone layer, is because CFCs stay in the atmosphere for a very long time. They're very persistent. So although the Montreal Protocol stopped the production of CFCs, we don't expect the stratospheric ozone to repair itself, that ozone to regenerate for at least a couple more decades toward the middle of this century. So we banned CFCs. It was a great example of an international treaty that worked. Then we had to find something to substitute them with. And so one solution was to use hydrofluorocarbons, HFCs. So again, be sure you know the name and the abbreviation HFCs. And it worked fine. It worked fine in terms of aerosols and refrigerants. The problem, HFCs are a strong greenhouse gas. So we know that CH4, H2O, CO2, we have some very clear greenhouse gases that we've talked about in the class before. And now we can add HFCs to one of them. They're not one of the main ones that we typically talk about, but this is an unintended consequence of the solution to ban CFCs and replace them with HFCs. So when we look back at practices, I think this is a great example of this practice number 7, this solution. So we know that this is increasing complexity when you're asked to describe a problem, describe potential approaches or solutions to that problem, look at the advantages and disadvantages and the unintended consequences, and then use data to select one of those solutions and to justify it. So I want to bring up a very clear misconception in a minute, and to do that, I'm going to ask for the help from this little video clip here, just the last part of it.
15 to 35 kilometers above Earth's surface, a gas called ozone surrounds the planet. The ozone layer acts as a barrier between Earth and ultraviolet radiation from the sun. However, pollution has caused the ozone layer to thin, exposing life on Earth to dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules for every 10 million molecules of air. But it does a very important job. The ozone layer acts as Earth's sunscreen, absorbing about 98% of damaging ultraviolet or UV light. But the ozone layer has gotten thinner. Chemicals called chlorofluorocarbons, or CFCs, are the primary culprits in ozone layer breakdown. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin patch, with the thinnest areas near the poles. The ozone layer above the Antarctic, in particular, has been impacted by pollution since the mid-1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the Northern Hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.
So I want to at this point, so hopefully that was a good review, that you should be able to at this point explain stratospheric ozone layer, its function, how we depleted it by the use of CFCs, and how the Montreal Protocol solved that problem for the most part. But I want to point out a very common misconception is that stratospheric ozone depletion is not the same as global warming and climate change. Because they're both dealing with the atmosphere and because there's some chemistry involved in both, sometimes students will implicate ozone depletion as part of climate change. But the depletion of the stratospheric ozone layer is not a direct cause of climate change. They're two different problems. And in fact, if you think about stratospheric ozone depletion, it's a problem that we've solved. We found the culprit, we banned the culprit, and we're monitoring the regrowth of the ozone layer. So this is a problem solved. This is a problem we're clearly in. But while they do have some interrelated components and characters, stratospheric ozone layer is about UV radiation, think sunburn, whereas climate change is about heat, being hot. So they're related, but they're two different issues, and you need to keep those very separate when you're talking about them on an FRQ. So this little last clip talks about the difference between the solution that we've made with stratospheric ozone layer and the continuing problem of climate change.
Humans have started to do the right thing in order to convert the chemical nature of the atmosphere back toward what it was before Industrial Revolution started.
It'll be some time before scientists can absolutely confirm that the ozone hole is actually growing over, but the signs are good. Unlike that other global problem, climate change. People in the Himalayas struggling this week against the sort of weather scientists say will get worse as carbon dioxide levels increase. It's so much more difficult. Our cars, homes, factories all contribute to heating the planet. This problem may not get solved at all. Roger Harrabin, BBC News. It was the
So clearly I'm a little bit more optimistic than that last sentence. I think that we can solve this problem. And I think by understanding what this course can tell us, we know what we should be doing or what we hopefully will be doing in the future. So let's do a quick check for understanding with some multiple choice questions, and then we'll do a quick summary and then jump into a practice FRQ on this topic. So the question says the main environmental effects of ozone depletion could include all of the following except. So I'll give you 30 seconds to chew on that. All right, hopefully you realized it was B. Everything else you can see is an increase in ozone depletion would be an increase in UV radiation hitting the Earth, and all of these things are in the biosphere that would be impacted by that, except for decrease in CO2. Next question says, which of the following human activities is most closely associated with the depletion of the stratospheric ozone layer? So take 27.25 seconds and look at that one. And the one that should stand out to you is refrigerators and air conditioners, because we implicated refrigerants as something that contains CFCs. And so when those are disposed of, and particularly when they're disposed of improperly, those chemicals can escape into the atmosphere. This next one says, which of the following substances is released by CFCs and catalyzes a chain reaction that breaks down ozone in the upper atmosphere? And hopefully you remembered our villain here was chlorine. The chlorine atom pops off of that CFC as soon as the UV radiation, the UV light hits that. So let's debrief and summarize where we went. So we talked about 9.1, stratospheric ozone depletion, and 9.2, reducing that depletion. So let's look at the specific essential knowledge statements from 9.1. So the first one talks about why the ozone layer is important for life on Earth. We've evolved along with that ozone layer. And then we talked about the CFCs, implicating them in the anthropogenic destruction or depletion of the stratospheric ozone layer. I do want to point out that it says natural factors such as melting of ice crystals in the atmosphere at the beginning of the Antarctic spring. So there is some natural degradation of stratospheric ozone that occurs naturally, but what we're focused on in particular today was the anthropogenic factors like CFCs. And what would happen if this depletion continued? We would have decreased or increased rates of skin cancer and cataracts in humans. So basically, because we know all this, we should be able to explain the importance of the stratospheric ozone to life on Earth. And if you haven't really looked at some of these unit guides yet, you should realize that these are the essential knowledge statements that you should know in order to do this thing, in order to explain the importance of stratospheric ozone to life on Earth. And then for 9.2, talked about the replacements, the HFCs, and some of the pros and cons of that. So based on that, we should be able to describe the chemicals used to substitute CFCs. All right, so let's do some practice here. So we're going to do an FRQ that's going to require some concept explanation. So just remember that this is science practice number 1, and this is asking you to write explanations that describe environmental processes. And your written descriptions should demonstrate that you've done more than just memorize the facts. It's one thing to memorize what a CFC is. It's another thing to be able to explain the role of CFCs in stratospheric ozone depletion. I always joke that my Nana might be able to talk about pollution in a general sense, but she wouldn't sound like she's taken an APES course. You need to sound like you've taken an APES course when you write FRQs. So again, to explain a concept, you kind of describe first, and then you get into more of an explanation. But if you see the word explain, like Ms. Fassler said, be thinking of what verbs can you use in your writing, multiple sentences, things like that. So here are our task verbs that I've mentioned every time so far. The 3 that we're going to look at today are describe, explain, and identify. All right, we are going to do the 2013 FRQ all about ozone. We're not going to do the whole thing, but we're going to do some big chunks of it. So in fact, we're going to do everything but B. And we're going to do it in pieces because I think it would be a little awkward if I just said, okay, take 15, 20 minutes and go write by yourself. So we're going to take it in chunks, take a minute or 2 for each one, then go over the answers. So the prompt says, and actually let me go back one, sorry. ozone, O3, is an atmospheric trace gas that occurs naturally in the stratosphere. Okay, we know that. It is also formed as a consequence of human activity in the troposphere immediately above Earth's surface. So those two sentences describe good up high, bad nearby. Sunscreen good on my skin, sunscreen bad in my stomach. The location of ozone in the atmosphere determines whether the gas protects or damages the environment. All right, so let's take a look at A. A says identify the type of solar radiation that is absorbed by the stratospheric ozone and describe one human health benefit that results from the absorption of this solar energy. So take a minute or so and we will look at the answer. Okay, so again, there's two parts to this FRQ, so be sure, let's look at both of them. So the first one says, identify the type of solar radiation. So you get 1 point for identifying ultraviolet radiation, UV, UVB, or UVC. So that's 1 point for just identifying ultraviolet radiation. Your second point comes from the benefits of that, the human health benefits of being very specific about humans. So that is causing less skin cancer, less sunburn, less eye damage like cataracts. So what is it blocking and what is that benefiting us? All right, C says, the Montreal Protocol of 1987 provided a global framework to phase out CFC production and use. Although the Montreal Protocol has led to a dramatic decrease in CFCs released into the atmosphere, stratospheric ozone destruction has decreased only slightly. So I says, explain the process by which CFCs leads to the destruction of stratospheric ozone. You may use chemical equations in your answer. So it says may, you don't have to. So take 1 minute and see if you can describe on your paper, or I'm sorry, explain on your paper how CFCs destroy the ozone, stratospheric ozone. Okay, take it a couple more seconds. So this is a really great example of the difference between being able to identify something and explain something. You may have remembered that CFCs were involved somehow, but can you explain it? So here's what we were looking for. This is worth 2 points. 1 point for a correct description of how the decomposition of CFCs. So the first point comes from UV radiation hitting the CFC and popping off a chlorine. So absorption of UV radiation by CFC molecules releases chlorine atoms, or you could have represented that with the chemical equation. So that's the first part, the CFCs becoming liberated, or the chlorine becoming liberated from the CFCs. The second point comes from being able to describe that free chlorine now breaks down ozone molecules, or you could have represented that as an equation. Okay, so 2 points there. All right, let's go to the next one. So CII says, explain why the rapid decrease in CFC emissions has not led to similarly rapid decrease in the destruction of ozone, stratospheric ozone. So take 30 seconds and think about that. All right, so hopefully you were thinking about the persistence of the CFCs. That's what I think of. So this is 1 point can be earned for a correct explanation linking the absence of rapid decrease in the destruction of the stratospheric ozone with one of the following. So you may have talked about how it takes a while for the CFCs to get up into the stratosphere, or the long lifetime of CFCs or chlorine in the atmosphere, or the continued release of other ozone depleting substances. So I would probably tend to hit this middle one in my brain, that these persist a long time. So even though we stopped it on a Monday, on Tuesday, there's still some up there. And finally, we're going to now go from good up high to bad nearby. So it says, identify a human activity that leads to the formation of tropospheric ozone as a secondary pollutant, and explain why tropospheric ozone levels peak in the daytime. So this question clearly has 2 parts. I recommend to my students, there's no need to restate the question, but you could say one activity that leads to the formation of tropospheric ozone is, and then identify it, period. And then go into your explanation of why it peaks in the daytime. So take about 40 seconds or so and jot down some ideas of what you might put for 3B. All right, so the human activity, now it's asking for a specific human activity, not just things in general. So anytime we burn fossil fuels, either in motor vehicles or electric power generation, we're putting those emissions into the air and releasing VOCs by doing something like pumping gases or using paints. Why does it peak in the daytime? Because sunlight is involved. This is a photochemical reaction. It's chemically started up. So we're looking for that sunlight answer there. And finally, E talks about the human effects, the negative health effects. Identify one ecological impact and one human health effect. So ecologically, you could talk about it damaging plant tissue or inhibiting photosynthesis. And then for humans, it is the irritation to the respiratory system, coughing, decreasing lung function, irritating eyes. So there's some clear ecological, meaning non-human, and then human impacts as well. All right, that's stratospheric ozone layer. Hope you enjoyed it, and I will see you next time, and don't eat sunscreen. Bye.